So here's a problem from the 2015 AP Calc BC exam. This is a calculator question, pretty typical of a lot of calculator questions that appear on the BC exam. It's dealing with parametric equations, so a particle is moving along a curve in the xy plane. Position of the particle, x coordinates determined by some function of t, y coordinates determined by some other function of t. What they provide us is not necessarily with x of t and y of t, but they provide us with the velocity vector for this particular particle. So we know that the x component of velocity is given by this, and the y component of velocity is given by this exponential piece. And then they go on to tell us that at time 1 we have a set of coordinates of 3, 5 for the position of the object. What part A asks of us is to try to find the x coordinate of this particle at time 2. So if you've been doing a lot of free response work, you've done a ton of problems that have been situations where you have a certain starting amount and then you integrate a rate of change to figure out what your ending amount is. So to find the ending position at time 2, and just the x, we don't necessarily need the whole set of coordinates, but to find the x coordinate at time 2, we're going to have to take the x coordinate that we know. So at time 1, we know the x coordinate is 3, and we're going to have to add on how much the x coordinate changes by integrating its rate of change across the interval from 1 to 2. Well, the rate of change of the x coordinate of position is the x component of velocity. Therefore, that's the function that goes into this integral. And it's a calculator problem, so if the calculator's in play, here's my TI-83 input, and there is your final result for part A. Part B says that between 0 and 1, there's a point on the curve where our tangent line has a slope of 2. We want to know what time this happens. So you need to know that to find the slope of the tangent line to a parametric curve evaluated at a certain time t, and I'm just calling that time A, you're going to need to still evaluate the rate of change of y with respect to x, because these graphs still occur in the coordinate plane. So when you developed your parametric ideas within your course, you probably derived this, and since then you've just used it, but the way you find dy dx on a parametric curve is you evaluate dy dt divided by dx dt. That's pretty simple to do here. They provide us with dy dt. That's the rate of change of y, so the y component of velocity. So that's what's going into this numerator evaluated at a. And then in the denominator, I'm taking the rate of change of x with respect to t and tossing that into the denominator. I want to know when this slope calculation equals 2. So I basically set this fraction equal to 2. This is a little weird. This is a parametric curve, so I'm sure you've played around with parametric graphing mode on your calculator. But what you can't do in parametric graphing mode is you can't solve an equation like this graphically. So what I did is I kicked my calculator back to function mode, and I graphed y equals 2, so that's obviously the horizontal line that you see right here. And then I also graphed this expression, and so when I graph this expression, I end up with this. I did shrink my window down, so I think I'm looking from like -1 clear up to 2. I was focused on the stretch of the graph between 0 and 1 though, and I do see a spot where my slope expression equals 2, so I use the calculator to find that intersection, and we have the time when the slope is 2. Part C deals with speed. So find the time at which the speed of the particle is 3. So you do need to realize how to compute speed here. So in your calc course, in your physics course, I'm sure you've done a little bit of resolving vectors. If we have the x component of velocity here and the y component of velocity here, speed is simply going to be the magnitude of that resulting vector, or if you complete the triangle as I've done here, it's going to be the value of the hypotenuse of the triangle. So it's going to be a slope calculation, excuse me, not a slope calculation, it's going to be a Pythagorean theorem calculation applied to these components as the legs and solved for the hypotenuse. So I have the x component of velocity squared, I have added on the y component of velocity squared, and then I've solved that for speed squared by taking a square root. So here's my speed expression for any time t. I needed to know when that speed expression is equal to 3. So once again, in function mode on the calculator, I graphed y equals 3, so there's your horizontal y equals 3, and then I graphed the speed expression that we just talked about, and I was looking for when the speed of the object was 3, and so I found the intersection once again and had the result. And then the final part of this asks us to find the total distance traveled by the particle from time 0 to time 1. So when you have motion that's only happening in a single dimension, to find total distance traveled, what you've probably done in the past is you've probably integrated the absolute value of velocity. Well, the absolute value of velocity is really speed. So what we're going to do in a two-dimensional motion problem like this is we're still going to integrate our speed expression, because speeds are only ever positive. Right? So you don't, to find total distance, you don't do that with individual velocity components because those could potentially be negative. So if you do something that makes all of your velocities positive, and in this case finding the magnitude, finding the speed does just that, we're going to integrate all of those speeds across the interval 0 to 1, and calculator's in play, so we can fire that into the calculator one more time, and we have our result.